we'll pick up, obviously, part 2 on Friday. We're going to continue to talk about gases. Last time we were here, we talked about, this is a box. It's a sealed box that's containing a gas. These are my gas particles, and to show that they have a lot of kinetic energy, I usually pick on one and give it an arrow. Of course, if we heat it up, then I'd make it go faster, so I get a bigger arrow. We talked about the 4 variables, P, V, N, and T. Let's just get kind of dry. Pressure, volume, number of moles, and temperature. And then we talked about various things, various sort of thought exercises where you take 2 and let them vary and keep the other the same. So we took the pressure and volume, we looked at number of moles and volume, and that sort of thing. And we're going to kind of pick up there where we left off. Now, these are 3 different laws that look at these 3 variables. 4 variables. Those 3 laws look at these 4 variables, and they do exactly what we did on Monday, where they look at a pair and have the other 2 stay the same. I jotted it down because I can never remember. But what these are all guides, by the way. But what Boyle's law does, what Boyle's law boils down to, is looking at pressure and volume. And what Charles' law does is look at temperature and volume. And what Avogadro's law does is look at number of moles and volume. Okay, so kind of like we did before. What these have in common, and we're going to kind of build up to it, is they are all looking at volume. So actually, we're going to look at these, Boyle's, Charles, and Avogadro's law, and then we're going to kind of link them all with regard to volume. So it looks something like this. Oh, sorry. Before we do that, I need to talk about this thing called ideal gas behavior. So we're going to come up with the ideal gas law equation, P equals nRT. Everyone knows that, right? And the ideal gas law equation assumes that those gas particles are behaving ideally. And there's 2 of those assumptions. Oh, by the way, have you ever heard this? You know what assuming does? It makes an ass out of you and me, potentially. Have you ever heard that? Assumption, ass, anyway. So assumptions can be dangerous. But we are assuming, for instance, that those gas particles are behaving independently of any other gas particles in there. Okay, so they don't interact with each other. No forces joining them. No intermolecular forces. The other thing is kind of weird. Everything, all matter has mass and occupies space. We are going to pretend as if those particles basically do not occupy space. That's to say that they are so small relative to the volume of their container, we're going to say that they occupy no space. Their volume is negligible relative to the volume that they're bouncing around in. Not bad, and actually in Chem 2, we're going to kind of revisit these these 2 assumptions of gases behaving ideally. But no intermolecular bonds, which that's kind of what we said a gas is, and that their volume is negligible relative to the container that they're bouncing around in. So Boyle's law, I already told you, looks at pressure and volume. So we used this proportionality symbol the other day. And Boyle's law is called the compressibility law of gases. Basically, we know that you can take a volume and you can make it smaller and smaller and smaller and smaller and leave those particles in, those gas particles just get closer together. As we decrease the volume, what happens to the pressure? It increases, yeah. So we have this sort of thing. It's an inverse relationship. And we can show that by using the proportionality symbol. And so we can either say volume is proportional to the inverse of pressure, or we can say pressure is proportional to the inverse of volume. It's the same thing. Okay, so those are inversely related. I want to take this one step further. We can clean it up and replace that proportionality symbol, infinity with pi taken out of it, with an equal sign if we introduce a constant. So here's what this would look like. So here we're going to call this constant some variable k, and we'll kind of revisit what that constant really is. But mathematically, the product, or the multiplying these two together, is always going to be equal to some constant. Because you told me if the volume goes down, the pressure goes up, and if you multiply those together, they're going to always be equal to some constant. That works. So that's Boyle's law. Charles' law, I said, looks at volume with temperature. Let's see, volume with temperature. What do you think? Now this again would be holding, now we're holding pressure constant and number of moles constant. So what happens if we want to keep the same pressure? If we increase the temperature, what has to happen to the volume? It has to increase. So here we have increased temperature, increased volume. They're directly proportional, so they should look like this. Now again, we're going to go ahead and clean it up and get rid of the proportionality symbol, introduce a constant, but this time it's not the product or the multiplying them together that equals the constant. It's actually the ratio that equals some constant. Okay? Mathematically, if one goes up, well, temperature goes up, volume goes up. Temperature goes down, volume goes down. That's assuming that your pressure is held constant and that you're not introducing or removing any gases. Cool. So actually I have a few figures, or one of my favorite figures is coming up with regard to Charles' law. This, there's actually one more column here. Now, remember one of the things we said Monday is that your temperature needs to be in units of Kelvin. It just has to be. You have no choice here. You have a little wiggle room with regard to volume and pressure, but temperature has to be in units of the most sophisticated temperature scale that we have, because there's an absolute zero there. And to kind of show you how this would work, we have some ordered pairs here. Notice, and this actually works. We start at our lowest temperature is 111 Kelvin, okay, and it goes up to 270 Kelvin, so that data is contained on that line right there. One of the things that you guys have done with your data this year is to, what did you do? If you had a line that, a point that fell on this curve, that would be interpolation. If you have a point that falls off of that line, that would be extrapolation. So here again, we're extrapolating. I think we talked a little bit about that on Monday. So if we get smaller and smaller volume, we approach zero volume at absolute zero. Isn't that cool? But, and again, we're going to kind of address this in Chem 2 a little bit. The problem becomes, if you take this box and you want to keep the same pressure, honestly, keeping the same pressure is why you have to reduce the size of your container, okay? So as we cool them down, they go slower. To keep the same pressure, we've got to make the box smaller. Or the box will automatically get smaller on its own if it keeps the same pressure. So if we go chill it down to absolute zero, basically your box has zero volume. The thing about it is you get closer and closer to zero volume. Now the particle volume, you're going to bump up against going outside of the assumption that the volume of your particle is negligible. Because now the volume of your container is very small. So the volume of your particle actually then, your assumption starts to fall apart. This one, I actually did the math. So finally we have these two columns here. These are right. I told my husband that. I'm like, are you serious? So I thought I'd go ahead. There will be some, the problems we're going to work today. Oftentimes you give them the temperature in Celsius, but you can't use it in Celsius. So remember how that works. See if I can make sure I get this right. A lot of times you need to go to Kelvin, and to go to Kelvin, you take the Celsius temperature plus 273.15. That works. And then sometimes you need to go back the other way. So if you want the Celsius temperature, you're given the Kelvin temperature, what you do is you take the Kelvin temperature, and from that you subtract 273.15 units. Okay, so I actually got two little equations there. All right, so Charles' law. Charles' law says that the volume and the temperature are directly proportional to one another. So make sure that you go with Kelvin units when you're working any sort of problem with regard to gases. Kelvin, Kelvin, Kelvin. Let's check out this little video. Your aunts or uncles didn't buy you an ant farm for Christmas? Oh my gosh. But if you did buy an ant farm, you get the ants in the mail. And the ants are kind of under-animated. They must have been like cold. They must send them with a cold pack or something. So your ants are under-animated. And that, to me, kind of reminds me of this little exhibit with regard to the effect of temperature, specifically cooling or warming, and volume. Well, the other thing, you guys didn't know that. You probably won't know this, but who was the... Oh, some night show guy. He used to always do this liquid nitrogen thing where he dipped different things in liquid nitrogen. It gets very brittle. Nitrogen is usually a gas, but if you cool it down and you compress it, you can make nitrogen into a liquid, and it's very cold. So in this doer right here is liquid nitrogen. So he used to like put roses in there and they'd shatter when they took them out. So anyway, the gas of interest is going to be the gas in those balloons. So here we go. So basically, you take these balloons and you put them in that liquid nitrogen, and those little gas particles, they slow down, okay, and the volume decreases. And so here they are right here. And so those will be like the ants as you get them in the mail. Then you take them out of their cold environment, and they become reanimated. So yeah, so anyway, no balloons were harmed in the making of pictures. So we're taking out the balloon, it warms up, those gas particles go faster, and the volume increases. I just think that is so cool. I'm easily entertained. So the last one is Avogadro's law, and it looks at volume and number of moles. And I think we looked at this before. Basically, to me, it's kind of like blowing up a balloon. As you blow up a balloon, you increase N, and then what happens to V? Yeah, it increases too. So they're directly proportional. So they look like this. And again, if we want to go ahead and replace that proportionality symbol with an equal sign, we introduce a constant, and it looks like this, where the ratio of volume to number of moles is going to be equal to some constant. So mathematically, as one goes up, the other goes up, one goes down, the other goes down, in the same way, so that constant is a constant. We looked at those three laws. Avogadro's law, looking at number of moles and volume, actually has some implication in some stoichiometric calculations. I'm going to kind of give you a couple of hints to how that would work. I'm pretty sure this little video is going to look at basically making a water molecule from hydrogen and oxygen. So, of course, a water molecule, just in case they don't do this, we could take, 2 moles of hydrogen plus 1 mole of oxygen, and that will give us does that seem right? No. So this is 2 moles, and this is 1 mole, and this is 2 moles. I'll put a G here, make them all in their gas phase, or this won't work. So this moles is proportional, I'll make to volume. Okay, that's my sideways. This mole is proportional to volume, and this mole is proportional to volume. So it's pretty cool. This is where stoichiometry comes in. As long as they're all at the same temperature and pressure, you could have 2 liters of hydrogen will react with 1 liter of oxygen to form 2 liters of water gas. So we can actually use their stoichiometric coefficients as relative volumes. Isn't that cool? And that's just because moles is directly proportional to volume, as long as pressure and temperature are the same. So that's what these videos, I think, are going to basically show you. Water. So if we have two volumes, I said 2 liters, but 2 volumes of H2, 1 volume of O2, when it combines together, we form 2 moles, so we get 2 volumes of H2O. Again, this is switching gears from making water molecules to making ammonium. And we said that this is the balanced equation where we have 1 mole of N2 plus 3 moles of H2 goes to form 1 mole of NH3. So that means we could look at the volumes this way too. I think this is kind of clever. This is an OpenStax thing where each balloon is the same volume as the other balloon. So we would have 1 balloon of nitrogen, 3 relative balloons of hydrogen would form, oh, I'm missing my 2 over here. Goodness. Now that's OpenStax. There's another error. Do you guys see this? Are you serious? It's not balanced with a 1 there. It should be a 2. People. It's like they dropped the ball on this chapter. Oh, grr. Okay, we'll have to send that one to Carl too. Okay. But are we good with that? That should be 2. 2. All right. So let's see. What do we got? We have Boyle's, Charles, and Avogadro's laws right here. So since we have them nice and neat, all volumes on the left, we could combine that volume and combine what's on the, or we could, those volumes would be the same, combine what's on the right, and it looks like this. This is the joint proportionality statement, where volume of any gas is proportional to the number of moles and the temperature, and it's inversely proportional to pressure, so we'll put that in the bottom. Well, we know that we can take any proportionality statement like this and turn it into an equivalency statement, replace that proportionality symbol with an equal sign by introducing a constant. And if we introduce a constant, dun, 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 this is what it looks like. Now instead of proportional, we have equal. Volume is equal to some constant K times the number of moles times the temperature in the Kelvin scale divided by the pressure. Well, I can't remember what I do. Now, I am very careful about this whole, it's simple algebra. And I call it flattening out. I may have talked about this earlier in the semester. But if I want to get K by itself, which is what I want to do, I cross multiply. I assume that V is over 1, and I take my V times P is equal to KNT times 1. That's the way I think of it. In doing that, if I want to get K by itself, then I need to divide both sides by NT. So this is how I say it. V is equal to KNT over P. I kind of think that is over 1, and then I kind of crisscross. I take these guys times each other and these guys times each other. So that means VP is equal to KNT. And if I want to get K by itself, I need to divide both sides by NT. So VP over NT is equal to constant K. And I am not a teacher. Well, as it turns out, we're ready, and we do this a lot in physical science. We come up with these awesome constants, and they're very special. This one's very special. Instead of the variable K, we're going to actually use the variable R. And I'm going to turn these guys around. So I have P over V, PV over NT is equal to R. And R is the ideal gas law constant. Ideal gas law constant. So again, what 2 assumptions we're talking about? The 2 assumptions we talked about earlier. there's a value for R, and I'm going to give you one value. Actually, when I was y'all's age coming through UNI, I learned it as a different R with a different value, but it had different units. A preferred way of the ideal gas law equation is this flat one. And I just think when I retire, I'm going to make songs. And I think this one needs a song too. PV is equal to nRT. It's the flattened version of the ideal gas law equation. These are both say the same thing, okay? If I were to crisscross, I'd get PV equals to nRT. Okay? So they mean the same thing. Cool. Well, we're about units in this class, so we're going to make sure that when we use this, now this is kind of like, I use the word plug and chug. In physics, there's a lot of equations where you just pop in the value for the variable and get the variable that you're after. And that's kind of what finally this is, plug and chug. Q is equal to MC sub P delta T. That was a little bit of plug and chug too. But when you plug and chug, you have to include the units. So if we go with units of pressure is atmospheres, but my other ideal gas law constant value for R that I learned, actually this was millimeters of mercury, but we're going with atmospheres. Volume is a solid liters, N is a solid moles, temperature we said was Kelvin. In all of that mess, we come up with set units for R. And the value for R that we're going to use is going to be 0.082058. Units are liters, atmospheres. It has 2 units in the numerator and has 2 units in the denominator. Moles, Kelvin in the denominator. So just for kicks, if we go ahead and it's called dimensional analysis, let's see if the units work like they should. So pressure, I have atmospheres. Volume, I have liters is equal to N, I have moles. R, I said the units are going to be liters, atmospheres per mole, Kelvin. And then temperature, of course I have units of Kelvin. I'm going to put units of Kelvin over 1, moles over 1. So I'm kind of liking the things that cancel here. Kelvin cancels, moles cancels. We have atmospheres, liters is equal to liters atmosphere. Okay, that's just kind of a quick and dirty, yep, everything's good. Okay? Plug and chug, baby. Okay. So we're going to work a couple of kind of straightforward gas law problems today. And what I like to do, and sometimes I draw the box, sometimes I don't draw the box. But what I usually do is jot down P, V, N, and T. Okay, so let's look at the problem and kind of tease out of the problem what we have. So what volume? So I'll find my volume and I'll write a question mark. What volume? So that's what I'm after. What volume? Well, now, we're dealing with carbon dioxide and we have the mass. So do you guys see where under N, under my number of moles, I'm going to put 0.20 grams of CO2. Do you see how we can use the molar mass of CO2 and the mass to get to moles? I'll put that under my N. Occupies a pressure of 732 millimeters mercury. So I'll find my P. I'll put 732 mmHg. And my temperature is looking like 22.0 degrees Celsius. I think the reason I like to draw a picture, and I said sometimes it's like stalling, it kind of makes me feel comfortable with the problem, but in a way it helps me take charge of the information I have. It's not just an And I think I have a touch of dyslexia sometimes. It's not just a bunch of words and numbers. It's like, oh, well, that's it, isn't it? So as we work this problem, kind of tell you the strategy you're going to see on the slides is, do you see where I have to get my pressure into units of atmospheres, don't I? From millimeters of mercury, if I'm going to use that value of R. I have to get my temperature into units of Kelvin, no big deal. I'm going to what? Add 273.15 units. I can do that. I'm going to have to go ahead and take the mass and the molar mass of carbon dioxide to get to moles. I can do that. So I kind of call these like front end sort of little conversions. Then once I do all that, I'm ready to plug into my ideal gas law equation. Now, a lot of times what we'll do is we'll take the ideal gas law equation, PV equals nRT, and we'll basically rearrange it and we'll isolate the thing that we're trying to solve for. So the question mark here is volume. Again, be very careful. You are in good company if you mess up these algebra steps. Happens all the time. If we start with PV equals nRT and we're trying to isolate volume, I can divide both sides by pressure and then rewrite that. Volume is equal to nRT over P. That's it. So that's actually going to be our target to plug into. No problemo. Our value of R, I'm going to jot this down here because I can never remember. And I can't remember, I think I will double check. Oh yeah. So on your final exam, like Jacob was asking, on your final exam, you're going to have some gas law problems. And they won't all be probably this straightforward. I'll kind of show you some other types of gas law problems. But I think I give you the value of R, I'm pretty sure. Oh, wait a minute, no, I thought, no. You need to write it down on your sheet. That's right, that's what I got. Don't count on me giving you R. On your sheet, you guys remember, you're going to be able to have a sheet. On Friday, I'm going to give you back your test on Friday, and then I'm going to give you a blank periodic table that you can go ahead, if you already started marking up a periodic table for the final, that's fine. It just has to be one like the one that doesn't have the names of the elements for obvious reasons. Okay. So on your final exam, you can bring a periodic table with notes on the back, and heck, you can put notes on the front with the elements too. Okay. And I would put P equals nRT on my note card, and I would put R is equal to that value because I can never remember it. 0.82, 0.58, and you're going to need to know the units, liters, atmospheres per mole, Kelvin. Okay. Let's see what we got. So in italics here is like what I said over here. Basically, we have some kind of front end fixing we got to do. We got to convert from millimeters of mercury to atmospheres. We got to take mass and molar mass to get moles. We got to take our temperature and convert it to Kelvin. We can do all that before we plug it in. So the molar mass of CO2 looks like this: 12.01 plus 2 times 16.00, 44.01 grams per mole. And so our first term now is going to be that 0.20 grams over 1. And we use the molar mass in, gosh, it's been so long since we did this, the flipped version, right, of the molar mass. 1 mole over 44.01 grams. Just 2 sig figs. That means that our moles is going to be 0.0045 moles. And sometimes if I'm working a problem like this, you know, I will show all my work, but sometimes I'll go back to my thing up here and I'll say, aha, you know, 0.0045 moles. You know, makes me feel like I'm accomplishing something. So the other fixes we need to do, let's go ahead and get our temperature right. So we're going to add 273.15 units. It's just, and remember, since we're adding, we're going to round according to decimals. What I started to say is it's kind of like I could have put 273.2 and it would have been the same thing as 273.15 because I'm only allowed 1 decimal anyway. But rounding it to 1 decimal, it looks like this. So 295.2 Kelvin And also on your thing that you bring to the final, you're probably going to want to write down the relationship between atmospheres and millimeters of mercury. Does anybody remember what that is? It is 760. It's an exact relationship. Yep. So let's go ahead and knock that out. Our first term is going to be that 732 millimeters of mercury over 1. We want millimeters of mercury to cancel, so we're going to put our 760 millimeters of mercury in the bottom of the next term and 1 atmosphere in the top. Rounding to, we are allowed 3 sig figs, remember, because this is an exact relationship between atmospheres and millimeters of mercury. So we're allowed 3 sig figs. We're going to take all 3 of them. So you're looking at 0.963 atmospheres. So now, as far as I can tell, we're ready to go ahead and take these 3 values and plug them into that equation over there. V is equal to nRT over P. But now, on your final exam, if you run into this, wink, wink, do you remember that your final exam is going to be multiple choice section, and then the last section is going to be problems? If you're doing this as part of multiple choice section, I don't care if you doodle you don't have to show me any work, multiple choice questions. You don't have to show any work. You don't have to show any work. Okay, but for the last section, if you're doing a problem like this, you have to show your work and include units. That's my rule. So it looks like this. In the top, we're going to put moles, and I might even put it over 1. 0.0045 mole over 1. The reason I would do that is because I have units in the numerator and denominator on my value of R. So value of R, 0.082058. Units of R are liters, atmospheres per mole Kelvin. Of course, now my moles can cancel, but it's more obvious if I had this over 1. My moles will cancel. And then the temperature we had was at 295.2 Kelvin. I would also put that over 1. So I clearly see the units of Kelvin will cancel here. So now we only have units of liters, atmospheres in the numerator. In the denominator, we're going to put that 0.963 atmospheres in the denominator. And now that will allow my atmospheres to cancel. I have units of liters. So this has worked out just great. So how many sig figs do I need to round this to? 2. 0.11 liters. Seems anticlimactic, but that's what it is. Dum, dum, dum. So even though we had to kind of clean it up, do some background conversions, that was probably about as straightforward as gas problems come. And as you might imagine, we picked on volume. We could have picked on anything. We could have picked on number of moles or temperature or pressure. So let's look at something that's maybe a little different. Not quite as straightforward, but it's a classic. We're saying classic. Oh no, it's a classic. So I'll do this one over here. I'll draw a box for my gas. Draw some particles, draw a little arrow, show it's creating pressure, it's compressible, it's everything. And then I'll do P, V, N, T. And the reason I think I do it in that order is that's how I kind of remember it. PV is equal to nRT. I just kind of take those. So when you guys way back beginning of semester did densities for a block and you did densities for a rubber stopper, you came up with units. Density is always mass per volume. Okay, that's what density is. With normal objects, you'd probably go with grams per mass, and for volume, you'd probably go with milliliters or cubic centimeters. With gases, they're so sparse that for volume, instead of milliliters or cubic centimeters, we go with liters. So usually, the density of gas is going to be units of grams per liter, just because it's so sparse. So let's see what we got here. What is the density? So I'm just going to put, I don't know where I want to put it. So I'll put density question mark, and I'm going to go ahead and put units of grams per liter. What's the density? They give us a temperature. I'm going to go ahead and write that 25 degrees Celsius down. Of course, I'm going to have to convert that to Kelvin. And they give us a pressure, which is already atmospheres. Yay, so I don't have to convert that to atmospheres. That was ready to go. But they don't give us anything else. Well, there's this other sort of density that involves the two variables we don't have anything for. Okay. It's called molar density. Molar density is a really common thing with gases. And like the name implies, instead of grams per liter, actually it's moles per liter. So this is a case, I know it's going to feel kind of weird, but this is a case where I'm going to rearrange PV is equal to nRT. I'm going to rearrange it so that I get my molar density, which is going to be what? N over V. I'm going to rearrange it and then work the problem. So that hurts my brain. So what if I divide both sides by V, I can get N over V, and then, hopefully I don't mess this up. To me, what I got is P left, and I have to divide both sides by RT, right? I should have done it more than one step, but okay. I can't spell either. Oh my gosh, I was helping somebody with a paper today, and I just could not spell. Okay. So I know the goal is grams per liter, but if we get moles per liter, do you see where we're just one step away from moles per liter? We can use the molar math to get to grams per liter. Molar density, and if I use that's the molar mass, then that will give me 2 grams per liter. That's how we're going to work it. So it is kind of a little different. Our pressure is ready to go. It's in units of atmospheres, which is great. We said the temperature is not quite ready, so let's go ahead and take 25 plus 273.15. And again, in this case, you could take 25 plus 273, and it's the same Dec, because you have to round it to 1. That's 1. The unit's 1 anyway. So we're looking at 298 Kelvin. We run into 298 Kelvin a lot. I don't know if you remember back when we did thermodynamic problems, but thermodynamic standard conditions is 25 degrees Celsius. So if that temperature rings a bell, that's probably why. Okay, so I guess we're ready to plug and check. So our molar density is moles per liter. So molar density is a ratio of N over V. In the top, we're going to have our pressure, which is 1.22 atmospheres. And in the bottom, we're going to have R, which is 0.082058 units of R, our liters atmospheres, over moles Kelvin. And then also in the denominator is that 298 Kelvin. Now unit-wise, what we have is our denominator kind of cleans up. Our units of Kelvin cancel in the denominator. Our units of atmospheres cancel between the numerator and the denominator. By my count, that leaves units of liters per mole in the denominator, which, bringing it out or unpacking it, that would actually, you have to flip it. So liters per mole in the denominator is equal to moles per liter. It just is. It's a math thing. So 3 sig figs. So we get our molar density is 0.0499, and units would be moles per liter. A lot of times when you work, actually these two are examples of it, because we needed to know that this was carbon dioxide over here, and we need to know that the identity of this gas. A lot of times you don't even need to know the identity of the gas, but we review these two cases. So, can you remember which gas we're working with? Is this argon?
Yeah.
Okay, good. So the molar mass for argon is 39.95, makes a great password. Okay, so now moles cancel, we're left with units of grams per liter, which is perfect. Round to 3 sig figs. The density in grams per liter for that gas is 1.99 grams per liter. So this is kind of a twist to using the ideal gas law, incorporating density. That's what I wanted to get. Okay, so we'll try to take a running start at it, and I'll try to refresh you what we talked about on Friday, and we'll pick up here on Friday. Any questions about? On Friday, also, I will give you a periodic table and also give you like 20 questions that like multiple quick questions, so you kind of know what the final looks like with the answers.
So, like, should we look at the test every day?
Should you look at the tests you've taken so far? It wouldn't hurt.
I'll go with the short answer.
Right. They will jog your memory. I would do that, and I would also look at those kind of lecture guides at the beginning of the. Yep. Yes.
Everywhere.